See, it doesn't shout at me that says like, hey, I'm recording. But we are. Cool. All right. So last week we went through, introduced our independent sample team. Okay. This is kind of the bread and butter, the basis of a big chunk of the analyses that we'll be running throughout the year, right? Our independent sample t-test, what we're doing is we're just evaluating we're wanting to evaluate differences in means across two populations where the population mean and standard deviation is unknown across those. So we don't have access to means or standard deviation of the population. If we did, we wouldn't need an inference test, but we don't. So we do need an inference test. So what we're going to do is we're going to go through and we're going to pull samples from both of those and see, assuming the null hypothesis is true, assuming that these samples were drawn from populations with equal means, what's the likelihood of getting of observing the differences that we had given the sample size that we've drawn? Okay. Our null hypothesis is that mean 1 minus mean 2 is equal to 0. Our alternative is that it's not 0 if we're running a two-tailed test, right? Basically, again, we're looking at, do we have evidence? Are we getting evidence from these data that the samples that we've collected were likely drawn from populations with different means? Okay. Once you talk about assumptions of our independent sample t-test, again, our outcome is continuous, or we can treat it as continuous. Our observations are independent. This is kind of one of those methods things, right? Making sure that within each group that scores aren't dependent on one another. The distribution of sample means for each population is normal, right? Again, this isn't necessarily about the observed the distribution of the data that we've got. We're making assumptions about this sampling distribution of those scores, right? But we always need to go through and take a look at the distribution just to see if there's wacky stuff that's going to throw our inference off. And then our homogeneity of variance, right? We're assuming, like a t-test assumes that, okay, we're saying that we're testing to see whether this population mean is different than this population mean, but we're assuming that the variability in whatever we're measuring across both populations is equal, okay? And that starts to be important for getting that t-distribution that we've gone through and using, right? If we assume that the both populations we're pulling from have equal variance, then our t-statistic works out fine. If that's not true, then we start to run into some problems, okay? Informal assumptions that we don't have outliers and that we're assuming roughly equal sample sizes across groups, okay? And then all of our auxiliary stuff. So we go through, talk about our formula and how in the calculation of our standard error, for this, we now need to take into account error from two different samples. We've got error in sample A, we've got error in sample B. Functionally, what this does is it doubles my standard error, okay? And Olivia, if I double my standard error, that's gonna make my standard error go up. What's gonna happen to my t-statistic?
It's gonna go down.
It's gonna go down, right? I'm dividing that by a bigger number. And if my t-statistic is getting systematically smaller, what does that suggest for the likelihood of me rejecting the null hypothesis? Am I more or less likely to reject the null? Less likely, right? My test statistic is going down, right? I'm less likely to hit that criteria, that benchmark, right? And so again, this all makes sense if we understand what's going on. Basically, noise sort of messes up, it reduces our signal. And basically with our independent sample t-test, I've got noise from not just one sample, but two samples. So we've gone through and that's starting to go through and impact the signal that I'm getting here, okay? Talking about kind of where this is coming from, sort of the demonstration of why our standard error is an additive function of those two, of the two populations that we're pulling from. Talk about when we run into different sample sizes, because we're almost always going to run into different sample sizes. Hopefully the difference in sample size is just maybe a handful of people, right? Or proportionally not that much, but sometimes it can be fairly substantial. And so wanting to go through and account for a pooled variance that's going to go through and sort of recognize that my larger sample in general is going to be a more precise estimate of the variability in my corresponding population. And so what we want to do is give that larger sample more weight in accounting for or capturing the variability in our samples. Yeah.
Can you go back 2 slides real quick?
Yeah.
One more slide, sorry. A lot of clicks, my bad.
Yeah,
Okay,
no worries.
this is right. So if you were to present the independent T formula for us, you wouldn't include that second portion of the numerator, right?
What do you mean?
The crossed out portion,
Oh.
like that's more just to illustrate that.
Yeah, I mean,
This assumption, right?
yeah, but you know, if Kate, I wanted to say that, and this is where we start getting into like some real big money, like calling my shot thing. Like, let's say that you said that I expect these populations to differ by 5 units, right? We could very easily test that. SPSS won't do that for you, but like all you would need to do is put in assumed mean or assumed mean under for one versus the assumed mean of the other, and then that's going to change that numerator a little bit. Is it going to change the denominator? No, right? So now all of a sudden we're not just testing it against 0, we're testing against some. And so what's that going to do to the likelihood of me rejecting the null? So now I'm not just saying the difference is not 0, I'm saying the difference is not positive 5.
Increase.
What's that?
Increase your likelihood.
What were you gonna say, Abby?
I just said I think it makes you a lot more likely to reject it because you're rarely gonna get something exactly equal to 5.
Right, but if I'm thinking about it, so that an overall difference, right? Like, so let's say that I've got just with standard stuff, I'm saying that like, oh, the difference is not 0, right? And I find a difference of 10, okay? And so now my numerator is 10 points. But now I say, I'm calling my shot, I'm saying like, no, I think that that this group will exceed my reference group by is bigger than 5 points, right? So now if this is 10, but now that's 5, what happens to my numerator? It's now 5, right?
Yeah.
So it's essentially, and this is why we don't do it, is because it makes it a lot harder, right? Well, probably we don't do it because we aren't precise enough in our science to know, like, to make it a determination. Like, I can't say like, oh, what I'm thinking is that survivors of sexual assault are going to differ on the PTSD checklist by at least 10 points relative to survivors of motor vehicle accidents. I would generally say, given what I know about responses to traumatic events, that the sexual assault survivors on average will probably have higher scores than the other, but that's just saying that they're not the same. That's a 0 difference. If I go through and I tweak that to say it's at least 5 points higher, then I would have, then we start to get into some other, like, so you start to get into not just saying not 0, like I'm saying that this will exceed 5 points, right? So now all of a sudden, this piece has to be a lot bigger in order for me to sort of change against that. We don't do this, but it's something that could be very easily done here. So yes, this generally does, the way we conduct our science, this typically does cancel out, but it doesn't have to, because then we could start getting into point estimates if we wanted. And I don't even know what would happen if you tried to publish that. So like, I don't know, so a reviewer would probably freak out unless you talk to them and said like, look, this is what we got going on. But yeah, does that kind of help?
That does, thank you.
Okay. All right, so once we talked about that, talked about calculating our pooled variance, right? So we go through and do that pretty simple formula. So now our t-test is going to be the difference in means over my pooled variance estimate divided by the sample 1 pooled variance estimate divided by sample 2. So just these numbers are the same. Like those are just whatever you've gotten there, right? And so then there's our degrees of freedom, right? Talked about degrees of freedom, we got scared, we moved on, and talked about effect sizes here, right? We've got Cohen's D, right, which is giving us a metric of the magnitude of effect in units of standard deviation. Now, Cohen just says, yeah, it's the mean of 1 minus the mean of 2 over the standard deviation. Cohen doesn't tell us what standard deviation to use. Cohen would say from a theoretical standpoint, we're assuming the population variances are equal. So you choose one, doesn't matter which standard deviation you use. One of those standard deviations is going to be smaller than the other one. And if we choose the smaller one, it's going to make our sample or our D bigger, right? So what we use as standard practice, well, you use classes delta, right? This is just using the standard deviation of the control group, right? So if I've got a strong, good comparison sample, a true baseline, like this is the state of things just in the natural universe, glasses delta is a really nice metric to use. What we see more commonly is if you see Cohen's D, it's probably what has been referred to as Hedges D, where we're just using the pooled standard deviation here. This is a nice kind of balance, right? And we're also using the same variance estimate that we use in the calculation of our test statistic. Hedges G is a perfectly good way to go through. And when you see Cohen's D, this is generally how people are calculating it. Okay. We also know, however, that for very small samples, Hedges G is going to be an overestimate of the effect size, right? And so we have Hedges unbiased G. Unbiased G is just adding this correction factor, right? Question is, when should I add the correction factor? When shouldn't I? I don't know, right? If the sample size seems small, maybe go through and do it. If it seems not so small, maybe calculate and see kind of what's going on. Try not to make your too much of a decision based on how much of an adjustment it is, right? I mean, but you can kind of go through and take a look to see the corresponding effects here. Right? So again, remember that we're interpreting these. We can just say, hey, here's the effect size at small, medium, and large based on this, right? That's a really poor way to go through and do it because again, even Cohen said, don't use these as hard and fast benchmarks. And we immediately did exactly that, right? Remember that what we're talking about here is differences across our estimates of differences in our corresponding population means in terms of standard deviations, right? And this is kind of useful because assuming a normal curve, right? I know what a standard deviation is. I know what 2 standard deviations is. I know what 1/10 of a standard deviation is. That helps me sort of start to understand sort of overlap or differences and stuff. Right?
So you
Yeah.
just know, like, how, after a power analysis, you know, if your sample's too small and you should do the Hedges unbiased or?
Nope, never after you run your power analysis. If you're in your power analysis, you should have a plenty good sample and just go ahead and run some stuff. We'll go through and talk about today some of the examples. Like if I've got cell sizes like 10 or something like that, like I mean, looking at my overall sample, if it's pretty small, I might want to go through and take a look. Because again, what we're trying to do is prevent, we already know our science is going to systematically inflate effect sizes, just the way we publish and do things, just trying to not overinflate stuff. Yeah, Haley.
I did have it. So is the Hedges G, is it more, I don't know why I'm like so stuck on this like effect size thing. I just don't know if I'm just confused. Is the Hedges G just more of like a means to an end for like Cohen's D? So it's like that, is that how you get to a Cohen's D? Like, is that what people?
Yeah, don't worry about Cohen's D hedges. I mean, it's basically, Cohen came up with kind of the idea, the formula, kind of like, hey, this is in theory how we would do things. This is just like saying, okay, well, we've got a lot of different choices on how we can go through and what we use as our standardizer. And this is going to be a big piece of this next assignment is choosing, like, and telling me, like, what was the standardizer you used for your effect size and why, right? And a lot of this depends on the methods, the context, kind of what's happening, right? So Cohen just says S, but there's lots of different S's. Hedges is just saying pooled standard deviation. That's a nice guess. That's a nice option. We kind of just split the difference between this. Makes sense to go through and do that. It's the same variance estimate we use in the calculation for test statistics. So why not use it as our standardizer? Okay. Now I would make an argument that why would we ever use classes delta, right? Like, well, I don't know if I'm looking at, I think something that, again, sort of just go back, because I know, Lindsay, you're in a lab where sort of outcomes are like physical characteristics that sort of people are generally, if I'm looking at saying average weight for someone in sort of eating disorder treatment or something like that, and I have a control group and I have a treatment group that's had some sort of intervention or something like that, right? And my control group is just a non-contact control. Like this is just where people are at in terms of mass. If they just kind of stay the same, this is just like the state of affairs out in the universe. Well, now all of a sudden I can say we're seeing have a standard deviation reduction in final weight or sort of a standard deviation increase in weight relative to this population where they're just at in general, right? And that has a lot of nice interpretive value, because if I work in this area, I probably have a reasonable understanding of how much weight varies just in general, right? So that might be a good thing. But let's say, flip this around, say Lindsay's going through and she's comparing treatment 1 versus treatment 2, right? Now all of a sudden I don't have a good baseline because I've done something to both of these. And so there's no really true group I can sort of reference that standard deviation to. And so in that case, Hedges is a great option in saying, okay, we're just going to go through and we're going to take a look at these, right? Also, particularly in situations where you might have unequal variances across groups, right? This is kind of a split the difference situation. Any other questions with the effect size stuff? Yeah, maybe.
You don't like, yes, no question, like set questions, but would it be better to just use the Hedges G instead of the Cohen's D, since we may
Okay.
not know that?
Ignore Cohen's D.
Okay.
Cohen's D is a theoretical proposition. Okay. Here we're talking about sort of these, because I don't know, if you say I just calculated Cohen's D, I'm like, well, I need to have more information. What did you use as your standardizer? You're like, well, I use the control group, or I use the pool variance spec. Oh, okay, that's cool. Right. So this is just Cohen's formula, but it's not. I've got to make a decision here, and as soon as I make a decision here, then I'd probably drop down into one of these. Okay. Yeah.
So when we're like reading literature and we see someone reporting like Cohen's D.
Yeah.
we-
Who the
it
hell
could
knows?
be any of
Oh.
those.
Yeah.
They're
yeah.
not always saying it's G equals or anything
Yeah.
like that, or.
No, and this is the thing, like, so when I'm publishing, because I teach all of you this, and this is important stuff and interesting stuff to me, I'll generally include a footnote. I say, effect sizes are calculated as, using the, pool variance across things, just so people know exactly what's going on. Generally, it's probably this, but if they don't know, if they don't tell me, I don't know, right?
Yeah.
And so, no, that's a fair question, and sort of trying to figure out, sometimes you can reverse engineer, if they got means and standard deviations, just calculate it by hand and see if it matches up with what they've got. If it does, they're probably got that. If it doesn't, now all of a sudden I got questions about how they went through and how they calculated that, yeah.
For glasses Delta, will you? How do we know if we have like a for real control?
It's a conceptual issue, right? Like you're just thinking about the design, like, basically it boils down to, do I have a control group that makes sense? Like there's something just as a normal state of affairs, right? So if you've got looking at confidence using, let's say, like just normal jury instructions, right? This is the variability that we see just with the standard jury instructions that people get all day, every day. And so this is a good control group, right? Or maybe you've got like this jury got this version and the other one got this version. They're not, I can't sort of say this is the better control. And so then maybe it's hard to choose something like that, and then you just drop down to that.
So like on our problem set, like a true control would be like, this is the reaction time for people who are not.
Yeah,
Okay.
yeah, if we were to do that. So we took that, and so in that problem set, we had taken that and presented that as like a one sample Z, right? Because we said, here's the mean and population mean standard deviation. But if we didn't know what the population mean standard deviation was and just gave that reaction time task and pulled a sample off of that, and we're using this as a 2-sample test, then yeah, that would be a great place to use a glasses delta. Yep. And then we start to get into the next lecture, some tricky things about calculating confidence bounds around stuff, and that sort of starts to play into some stuff, but we'll get to that when we get to that. All right, so we went through our example, just hand example, talking about influence of educational programming on high school outcomes. There we go. Just gotta be pointing in this direction. Went through our hand calculations, effect sizes, and then kind of put all this together, right? Talking about how precise, evidence against the null, practical impact, all these things I'm wanting you to kind of pack into these interpretations of flesh this out to make it a much more interesting and fruitful endeavor than just saying there's a difference, or this group was different than that group, which is boring and lazy. Yeah.
How do we get the S and the, yeah,
We sort of remember those are all just calculated straight from your p-value, right? So again, so previous slides, you've got formula for S value and base factor, right? And then in this next problem set that you got here, you can calculate a slick little Excel sheet that you can go through and use for rapid calculation of those things. Yeah, Johnny.
On the midterm, if we are asked to calculate the S value of the VFB, will we be just given the P value?
Yeah,
Okay.
yeah. And it'll be something that's not P less than 0.001 because you couldn't calculate anything off of that, right?
Yeah.
But this is where you need to make sure that you've got a calculator that's not your phone that has like BASIC and natural logs and stuff like that. So you can go through and make sure that you're calculating stuff. All right. So that was our sort of recap, but hopefully sort of this helps get us centered and sort of ready for this next piece. What happens if our estimate, if our population variances aren't equal? Okay, because remember we said this is an assumption of our t-test. We're assuming that the populations that we're sampling from have equal variance, but like what if they're not? Are we just SOL and then we can't run t-tests, right? Well, not exactly, but it is a problem, right? The problem is the sampling distribution of our t-test. Right, the sampling distribution of our T that we know and love, right? We'll call this saying, so then here is T equals 0, 4 degrees of freedom equals 50, right? Remember T is a family. T is a family of distributions. T isn't just a distribution. Z distribution, Z is just Z, right? T is a family of distributions. The shape changes a little bit based on the degrees of freedom, right? And so I have a sample of 26 and a sample of 26, and I know across repeated samplings of those, if I were to calculate T statistics for all possible samples that could be drawn from each of those populations of a given size with degrees of freedom 50, this is the distribution that T statistic would have, right? But what happens if my variances aren't equal? This is all predicated on my variances are equal in my population. Well, what if it's not? What if I have evidence that the variances of these two samples, or the populations from which these two samples were pulled, likely do not have equal variance, right? What happens is that now I've got a test statistic T that doesn't follow this distribution, follows some different distribution, because I violated the rules. And now I've got a different distribution than the one that I want to use to go through and test my stuff. Why is this problematic? Why don't we just say like, oh, well, close enough? Are we comfortable with close enough? Yeah, why not, Olivia?
You already called on me once.
It's all right. That's what happens randomly.
Can you repeat the question again?
Yeah. So why is it problematic if the test statistic that I've calculated, because it's calculated based on populations with unequal variances, don't follow the T distribution that are in our tables and things along those lines?
Because you can't standardize it.
Yeah, and so I've got problems with standardization. Yeah,
We can't apply the same assumptions to it.
we can't apply the same assumptions, right? And so I'm getting a very, very specific p-value that's p equals 0.0123478, something like that. I went from target shooting into a game of horseshoes, right? Where now all of a sudden but I'm still reporting it as if it's crazy precise, but the test statistic I've calculated isn't following the distribution that I'm testing against. We've got a mismatch. And so now all of a sudden, all of these inferences that I'm drawing are no longer actually valid because all my stuff is fine if I play by this set of rules, but now I've decided to play by a different set of rules. And so now all my inferences are out the window, right? We talked about this before, right? If we have, we're playing soccer and we sort of have multiple times and people are going through and so they go, all right, this is a better team than that because sort of across multiple games, they've won more things than that. Like, okay, right? And we all assume that that's probably a fair way to go through and do things. But now, how many people are on a soccer team?
I don't actually know, but
How
like.
many people
Is
are
it
there?
Yeah.
And it's like on the field at once?
Yeah, on each team. 11? Is that true?
I think it's
11.
10.
It depends. Well, you have how many are on the field.
And the goal
Yeah, how many are technically on the team.
Okay.
I mean,
Dressing too
it's 11
complicated.
unless you get a red card, then it's 10.
Okay, let's say 11, all right. So now all of a sudden, okay, but now,
There you go.
now instead of 11 people on both teams, like one team gets 13 people and the other one has 11. And now all of a sudden, the group with 13 people keep winning over and over again. Am I super confident that that's the better team? No, because all my rules just got thrown out the window because I started violating them and now I don't have as much confidence in the interpretations that I'm drawing from things, right? Same thing here. T-tests, our beautiful t-tests, our beautiful family of t-distributions work great so long as we have populations, pulling from populations with equal variances. But if they don't, what ends up happening is now I have a distribution of a t-statistic that's not known, right? I wish I had another ghost thing. We have a paranormal. We got a distribution that doesn't follow the rules that what I'm testing against, and so all of a sudden it starts to impact the accuracy of my inference, right? So some different ways that we've gone through and addressed this historically. The Behrens-Fisher solution is table distribution of T prime, but just for specific numbers of distributions. Like back in the day, like okay, well, like if there's like these differences. What I'm gonna do is I'm gonna table certain combinations of what that T distribution will look like under these conditions. And so then this is what we can go through and test against in terms of identifying our critical values and p-values and things along those lines. Problem is, there was only limited number of different types of distributions. Like our population variances can differ in all sorts of ways across all sorts of different sample sizes. All those things are going to impact my distribution, my T distribution. So this isn't a super efficient way to go through and do things. The way we sort of do things now within SPSS and other programs, and this is kind of our go-to, something we call a Welch-Satterthwaite solution. And what we do is we assume that T prime, okay, T prime is the distribution of our T statistic when we have unequal variances. So not T prime. But what we do is we assume that T prime is a member of the T family. We just don't know what degrees of freedom it corresponds to, right? So I'm saying I've got 26 people in my first sample, 26 people in my second sample, which should give me a T distribution with 50 degrees of freedom. But I've got a violation of homogeneity of variance. And so what my assumption is that I have a member of the T family. I just don't know what measure, what version of that family I have. It's probably not 50. It's something, but I don't know exactly what it is. And so what we do then is estimate with this the degrees of freedom as a function of the sample variances and the sample size of each group. Okay. So what we'll see in this in our output, equal variance is not assumed. What this is it's this Welch-Satterthwaite solution that's saying, okay, here's our test statistic, and we're going to compare it to a T distribution with some degrees of freedom. We're just adjusting the degrees of freedom on there, right? So we're going to choose a T distribution. It's just not the T distribution that we would choose if we had not had a violation of homogeneity of variance. Okay.
With the homogeneity of variance and Levine's test, isn't it when you, the statistic, but you may answer this, the statistic, when you look at it in the output, if it's like, if the p value,
Yeah.
like what you're,
Well,
all right, I'm just gonna
yeah.
stop then.
No, you're exactly right. And we're going to get that.
Okay.
Because what we do so the question is, do we need to go and fall back on this solution? Do we have evidence that my, the variance of the populations from which these samples were drawn are likely not equal, right? And what we have is kind of standard. It's not a perfect test, but it's what we use called Levine's test for homogeneity of variance, okay? And what we do sort of quite literally with this test is what we do is we replace each score with a deviation from the sample mean, okay? So I've got group A, so I create a deviation score of every score in group A from the sample mean, and every score in group B from their sample mean, right? And so I'm gonna have a metric of deviation scores. We either take the absolute value of those or square those values, right? And then what we literally do is we run a single, or that should be, I changed that and I made it. Well, so you have it right on yours. My computer died and froze up, and that's why that's still there. We conduct an independent sample t-test, right? So we look at the mean of deviation scores for group A, the mean of deviation scores for group B, and in a single sample t-test. If we fail to reject the null hypotheses, it says that the possibility of those deviation scores being equal is sort of reasonable, then we don't conclude a violation of homogeneity of variance. But if we do see that the deviation scores in group A are likely different than the deviation scores in group B, because we're using a means-based test to test variance here in terms of that deviation score being a metric of variance. What we would then do is conclude that we have a violation, and then we would fall back on our well-settled solution here. Okay, so this is a situation, and this will come up on occasion. Are we hoping for an opportunity to reject the null, or are we just hoping that we don't have enough evidence to reject the null and can proceed as if things were not problematic? Okay. So we'll go through and in the example, go through and talk about this and kind of show you what's happening and stuff. Okay, yeah.
I was wondering why you don't just always do a test for homogeneity of variance. Why don't you always like make sure that?
Oh, you will, and that's why, it's
Okay.
why it just, in SPSS, it kind of comes up standard. And we would go through and take a look. And it's hard to know in terms of like our published. Here's the thing, what happens is if you have a violation of homogeneity of variance, hopefully you're just dropping down to equal variance is not assumed, just interpreting that. Some, like a lot of times, most times people aren't reporting that, which they probably should. Problem is that your degrees of freedom get kind of screwy, and so there's some stuff going on with that. But yes, for this class, we'll always want you to be very explicit on which test that you're going to use. All right, thinking about for our independent samples t-test, we talked about our assumptions, right? The question is under what circumstances do we start to become concerned about violations of assumptions and the potential impact that it has on our inference? If I violate that homogeneity of variance test, if I have relatively equal ends, it's probably not going to have that big of an impact on my outcome. It's probably going to be fine. Okay. If I go through and I have some non-normality in my scores, right, in my observed data, but I've got a reasonable sample size and distributions that aren't sort of opposite shaped, right? If they're kind of similar, even if I've got some kind of ugly data, as long as it's ugly in the same way, I'm probably going to be kind of okay with that. Okay. Where we start running into problems is when we start doubling down on types of violations, right? So if I've got my data have different shape and unequal variances, now all of a sudden I've got a problem. Okay. Particularly problematic with severe skew in opposite directions. If I have one, group A has a severe positive skew and group B has a severe negative skew, I don't have equal variances across these two. That's a recipe for who knows what. Like I'm gonna have to start looking at possibly needing to use some transformations or something like that, right? Just because my data are skewed doesn't necessarily I have a concern, right? Because our assumption is about homogeneity of variance or distribution of sample means, right? But, and so if I have decent sized samples, those variability, homogeneity of variance looks kind of similar and everything's skewed in the same direction, that's fine. But if things are going the opposite direction, I've got different variances. Now I've got 13 guys on my team and we're using a different ball and the ref is randomly red carding the other team for no reason at all. Like everything's going bonkers, right? Like we don't understand what's happening, so that will impact things. Unequal variances and unequal sample sizes, okay? If I've got the violation of homogeneity of variance and very discrepant sample sizes, now all of a sudden I've got a problem, right? Because when I use my pooled variance, what sample is going to get more weight into it has more influence on my standard error, the bigger one, right? So if my larger sample has a larger variance, what's gonna happen is I'm gonna end up with a too conservative of a test, right? The sample that's bigger has the bigger variance and it's gonna swamp out the smaller sample. And so I'm gonna have a bigger pooled variance. And if I enter a bigger pooled variance, what's gonna happen to my standard error? It's gonna go up. My standard error goes up, what happens to my t-test? Goes down, right? And so we've got a problem. If my bigger sample has smaller variance, right? Again, it's gonna add in my standard error, my variance estimate, my pool variance estimate is probably gonna underestimate some variability in my other sample. Or in the other corresponding population, so my pool variance is gonna be too small, which means my standard error is gonna be too small, which means my test is gonna be too big, right? And so this is where starting to think about conceptually what's going on and then nuts and bolts of this is gonna help you kind of remembering and keep things sorted out. Well, we've got problems here. If I've got violations of normality and small sample sizes, now all of a sudden I've got a problem. Generally, you don't have to be too choked up about non-normality in our data, so long as we have reasonably sized samples. But if it's really severe and I have small samples, now all of a sudden those skew, those extreme values, that's gonna start dragging my means all over the place, right? Because I don't have enough sample size there to kind of back that up. And now all of a sudden I'm gonna have problems. Yeah, really.
Is that even a circuit? So like you say, if there's the minimal impact of heterogeneous?
What's that now?
The very first one?
Yeah,
No, up above robust, where it says assuming equal sample sizes between, like conditions.
yeah.
Is that even if your sample, so then when you consider if you have what if they're small sample sizes but equal? Like,
If there's small sample size and equal homogeneity and no violation. of homogeneity.
I guess, yeah, so I guess it was, never mind,
Okay.
assuming, yeah, because I was thinking like the two conditions.
Okay, cool, yeah. Hey, did you have a question? Okay, we'll get back to it. Mandy, yeah.
I just wanted to like make sure I'm getting this right. So for like the unequal variance and unequal sample size, for the too conservative, a bigger pool variance will result in a bigger standard error and the t-test will go down. And then for the other one, smaller pool variance. So then the standard error is small and the t-test will go up?
Yep.
Okay.
Yeah.
Thank you.
Yep, and just working with these ratios, right, like how all this works, starts to be a nice way to sort of not just like trying to memorize a bunch of rules. If we know kind of how the system works, then some of this stuff starts to make some sense. Okay, so here's our example. So we say investigators interested in sex differences in marital satisfaction in motor vehicle accident survivors committed to long-term heterosexual relationships. 22 men, women, 5 men meeting diagnostic criteria for PTSD subsequent to motor vehicle trauma complete Block-Wallace marital adjustment test. Scores range from 2 to 158 with higher values indicating greater relationship satisfaction. Participants also completed the Marlowe Crown social desirability scale 0 to 33 to assess differences in the tendency towards socially desirable responding male and female survivors. Based on research, investigators hypothesize that women will report greater levels of marital satisfaction relative to men. Tendency towards socially desirable responding is expected to be similar across groups. Okay, so who are our groups in this example? Yeah. All right, so married men and married women who've been in car accidents, right? And so this is important to start thinking about in that hypothesis statement. Who are we actually trying to refer to, right? We're talking about men and women who have been exposed to traumatic car accidents, right? Married people, married heterosexual people in long-term relationships who've been, and so you can start to see sort of how this starts to change our target population and thinking carefully about that. Okay, Allison, what are our outcome variables here?
Scores on the like marital adjustment test
Mhm. So we've got marital satisfaction and what else?
and the social desirability.
Social desirability, okay? So we've got a couple of different tests that we're gonna go through and run, all right? And so then this is just all the stuff that we that are normally due, right? And we'll go through that. So what we're gonna do is we're gonna start and pull up your MBAT test. Set here. And then also. Your independent sample test screening. That you've got there just as, so this worksheet is what we're gonna, be working through. In this example, okay? So what we wanna do first with our, in terms of our screening, what do we wanna do first?
Missing values.
Yeah, take a look and see if we got what we got in terms of missing values, right? So here we've got participant sex, here's PTSD, do we care about that? Nope, not part of this study. Care about so this thing, not part of the study, but we do care about our lock wash, right? So I'm gonna go through and right click, sort ascending, okay. And I could do the same thing for this, but I already know what's gonna happen because it's not that big of a set and I can already see it, right? So we've got case number 132, it's missing data. Can we include that person in our analyses? No, we sure can't. So what I'm gonna do is I'm gonna have a sort of my side note and say, case number 132, missing both Lock Wallace and Marlowe Crown scores. I'm gonna go through, save as, I'm gonna save it as scrap, or you can save it as working set, whatever you want to. So I'm not fooling around with the actual data. Okay, and I'm gonna go through and just clear that out. Okay, so got all of our data here, looking pretty good. Okay, now we're gonna go through and we're gonna start to take a look at plausibility, distributions and things along these lines. All right, but how many populations are we working with here? 2 populations. Does it make sense to start combining those populations when we're looking at things? Nope, it sure doesn't. Okay, so what we're gonna go through and do, ladies, are you all right here?
Yeah, I'm just catching, she had the wrong one open it, and then you're gonna delete this one.
All right. What we're gonna do then is make sure always for our independent sample t-test, we gotta split these groups apart because they're different populations. We can't mix them together, okay? So what we're gonna do, if you, again, this is just, all this is included on your screening here. What I'm gonna do in SPSS, I'm gonna go to data, and I'm gonna go down to split file. Okay, you choose split file, and what do I wanna split my file on? Gender, right? Because that's my grouping variable here. I'm gonna hit organize output by groups. You can hit compare groups, it just kind of changes like what it looks like. It's not too big of a thing. And then what I'm gonna go through is I'm gonna go through and I'm gonna hit paste. All right. So what we've got is a command in SPSS that's gonna go through and split my file based on this grouping variable. So I'm gonna hit double asterisk and I'm gonna say split file by sex. Make sure that you've got a space in between there, because if you don't have a space for whatever reason, won't read that. So go through. Now, when I go through and I hit the split file, what it means is so long as that split file is on, any analysis I run, it's going to run it separately for men, it's going to run it separately for women. Okay, and this is a very helpful thing as we're going through and trying to go through and screen our data. Okay, so I'm going to go through and I'm going to run this. All right, and now my split file is on. Okay, so now what I'm going to do is I'm going to go to analyze. We go to descriptives. We go down to descriptives. Choose that, and what do I want to look at descriptives on?
I just had a quick question.
Yeah.
Is there a way to like see that it actually split it? Like,
You'll
it
see-
does
yeah,
it
we'll-
look different?
We'll get there in a minute.
Okay.
Okay, you'll see like my gender variable is now worse sorted.
Okay, I had
Right.
already organized mine, so nothing
Yeah,
changed.
And
Okay.
as soon as you start running stuff, you'll see it. Okay. So what are my outcome variables I want to look at here?
Oh,
Mary.
some Milo.
Yeah. Block was marital satisfaction, right? So drop that over, okay? And so what I'm gonna do first, I'm gonna hit save standardized values as variables. So I'm gonna click this right here. And then in options, I'm gonna request skew and kurtosis values. I'm gonna hit continue. And then I'm gonna paste. And so now again, if you want to do this, so I'll go through and comment here, looking at more men and women. After a while, we kind of be able to just look at, once you get familiar with the syntax, you'll be able to just look at it and know, like, okay, I see what's going on here. Comments are a nice way early on to just kind of remind yourself what's happening. So if I go through now and I run this descriptives, you see here what I'm gonna get. I'll pop it up here just so we can see it a little bit easier. So it looks like on your handout, I use this as compare as opposed to look at. It's doing the same thing, it's just sort of making the format look a little bit different here, okay? But what we have is we have our distributions for men and for women, right? Now, Kate, if I didn't have that split file on, it would just give me all of it. And so I would know, oh, whoops, I gotta go back through and do this, okay? So if I go through Daniela, what am I seeing on this, on these distributions here? Let's start with men. What are you seeing in terms of men?
Men. N is just the number of people.
Yeah.
right? Okay.
Do we like 5?
Very small. Yeah,
That's,
like,
that's really small, right? So we've got a small sample here, right?
yeah.
Now let's go through and see, what about our min and our max? Are we comfortable with that?
Yeah, that's a very big difference.
Well, let's go through and take a look. So what we want to do is making sure that all our scores are in balance, right?
Okay.
So if my Lock Wallace ranges from 2 to 158, my Marla Crown 0 to 33,
Yeah, that's not.
they're all in balance, right? Looking good there, okay? What about my skew and my kurtosis values here?
Is there like, I don't remember the guide for skew and kurtosis. I know one is the platypus thing and one is the other. But I don't remember what that.
What are our general like sort of benchmarks for skew and kurtosis? Yeah,
2.
yeah, plus and minus 2, right? So are we sort of, do you have any concerns about skew?
It's negative, so yeah.
No, it's negative, but what's the absolute value here?
Oh, it's still below 1.
Yeah,
It's fine.
we're fine here. What about our kurtosis values?
That one is over 2.
Okay, so here's the thing. Our kurtosis values are over 2, but remember, like two doesn't rule me. Two is not the boss of me. 2 doesn't get to tell me what to do, right? 2 is a guideline that I can go through and think about and use carefully. Now I've got negative kurtosis. What does that suggest about my distributions? Yeah, kind of boxy, right? I don't have those tails with the negative kurtosis.
The platy.
The platycurdic, exactly. Looking like
Platypus.
those platypus, right? Lindsay, how many people do I have in these two groups?
5 men and 21 women.
Yeah, are those big groups?
No.
Okay, so thinking about what are the types of things that are influencing these scores? So yes, these are sort of like larger kurtosis values that suggest a noticeable deviation off of normality, right? But taken into the context that I only have just a handful of scores, it's really hard to get a nice, cute, normal distribution with just a handful of scores, right? Things are kind of pop up where they're gonna pop up. So I'm probably not gonna freak out too much. It's probably something worth noting. We have some evidence of negative kurtosis in these data, but I'm not gonna get too worked up about it quite yet. Okay. Same thing, Abby, what about if we take a look at our women, what's going on here?
Yeah, so let's see, I'm gonna look at the pictures again. So for the woman, is the Lock Wallace one the highest range out of, oh no, I'm looking at the wrong one, 158, so no, that's good too.
Okay.
And so then, let's see, both skew and kurtosis are less than 2.
Yeah, right. So it's not perfect. I wouldn't call it normal, but it's not anything that would start to raise red flags that would make me say, oh, whoops, I gotta pump the brakes. I gotta think about some crazy ass transformation or something along those lines. This is kind of basically what's going on. What's the biggest concern, like looking at this descriptives? I'll call you were wanting to answer, you looked at it.
No, I wasn't.
Yeah,
You talked about this beforehand. I need to stop doing this. The sample
the
size.
sample size, exactly, right? I like that your cognition is like you're
I
talking to yourself.
don't. I think it-
You always have the right answer. So
I'm gonna
yeah,
stop.
the sample size is the biggest issue with this, right? I've got some small samples here. And so that's probably gonna be the biggest thing that I'm starting to worry about, okay? So what I'm gonna do now is I'm gonna go to graphs. I'm gonna go to chart builder. And ask me a bunch of stuff, okay, whatever. But what, actually, you know what, I'm not gonna do this because what we could do if you wanted to, is I could go through and I could choose histogram and pull this down in here and do that, right? Or I could go to box plot and say, I wanna look at this and do these different things. But it's gonna be a lot of different steps that I need to go through and work through. And so that's actually not a super efficient way to do things. So what I'm gonna do instead, I'm gonna go to analyze. And I'm gonna go to descriptive statistics. And I'm gonna go to explore. And here what it's gonna do is I'm gonna go through and say, I wanna go through and I wanna look at my Lock Wallace, I wanna look at my Marlowe Crown. Put that in my dependent list, okay? Then what I'm gonna do is I'm gonna take my grouping variable, my gender variable, and I'm gonna drop that in my factor list. What this is gonna do is it's gonna tell SPSS to give me graphs, distributions, things like that separately for these two groups, okay? And then what I'm gonna do is I'm gonna take this label cases by, and I'm gonna drop my subject number in there, right? That's just kind of a nice thing for in SPSS for my box plots. Any of those things that are falling outside of 1.5 times the interquartile range, it's gonna label those with my participant number. If you don't click that, it's still gonna label them with numbers, but it's the case number where they're at in the file. And what you'll do is you'll forget to do that and report the case number or the order number as the participant number, and then that'll be all off. So just make sure that you're sort of getting this stuff here, okay? In terms of statistics, we just need the descriptives. We've already got them, but it'll give it to us anyway. What you want to do is go down to plots. Unclick stem and leaf because we don't, I don't necessarily care about that. But we'll go through and click histogram. Okay. I'm gonna hit continue. And now I'm gonna hit paste. Okay. All right. And so if we go down through, what I'm gonna do, Kate, is I'm gonna do something that's gonna give me an error, just so you can see. So I'm gonna go through and I'm gonna run this examine command. Oh, it didn't. Oh, I went through and did it. What'll happen is if you go through and run, oftentimes if you run that without unrunning the split file, it'll go through and because you already split file, and so it'll try and run split file for the women group or cross gender, but that's no longer that's a constant now, and so it'll do weird stuff. So if you want to turn your split file off, just go back to your data and just sort it. Right? As soon as you sort your data, it turns that split file off. Okay. So now what you can go through and do, if we go through and we run this, it'll be probably more efficient. Yeah. Okay. So here, this is giving us information for across men and women for the Lock Wallace, the Marlowe Crown. This is giving us a whole bunch of far greater number of descriptive statistics for each of these groups. It's giving us quartiles, min, max, range, confidence bounds, things along those lines. We don't necessarily need any of this because we've already gone through and looked at the stuff that we're interested in. What this does do though is it gives us a nice efficient way to go through, get our histograms and get our and our box plots. Okay, so here we go. We've got our histograms for men. Jalen, how does that histogram look? What does this histogram look like
I
here?
hate it.
Yeah, I hate it
Do
too.
we trust their groupings of stuff? Okay.
Don't worry about it too much. Again, how many people did we have in this sample? Five, right? So this is probably about the best that you're gonna get, right?
Okay,
So if we're looking at this, right, like this looks like a really wacky
yeah,
graph, right? But we can now start to see why we got that negative kurtosis with this, right? It's very clearly kind of boxy, right? But we do know, so we interpret this within the context of knowing that we've only got 5 people in the sample. So it's ugly. I don't care for it, but
trust.
yeah, it's what I would expect. I mean, it's not so much a trust thing as in these are just what these data look like with only 5 people in there, right? So we would go through and say, certainly it's sort of kind of boxy, but again, we've only got 5 people in there. So we're not gonna get too worried about it. With our, among our women, what are we seeing here in terms of our marital satisfaction scores?
At least they're unimodal.
They're unimodal, kind of. What's maybe going on
You
here?
almost have 2 humps though.
Yeah,
Yeah.
right?
That's what counts.
Yeah, no. We got kind of we got a major mode and a minor mode here. And it's hard to know what to do with this, right? Because we've only got 20 people, right? And what's it, 21? And if we were to go through, if Johnny were to run this in state, I'm not sure that you would get exactly the same thing here. But anytime we see a bimodal distribution, Haley, what are we thinking is a possibility?
And so we're saying a bimodal distribution.
Anybody help her?
Can you repeat what you said?
Yeah, anytime I see a bimodal distribution, what's the first thing I should maybe wonder?
There's something else with like dividing the groups.
Yeah, that maybe I've combined a couple of different distinct populations, right? If I'm seeing that bimodal distribution, I'm wondering, have I accidentally collapsed a couple of different populations that have different features with this? Yeah.
For instance, like age in this situation, maybe.
Age is a good one. I don't know. That's a good guess. No, I think that I'm not exactly sure if age is kind of continuous, but if I happen to capture sort of maybe some younger adults and some middle-aged adults and things like that, knowing this area, what I'm wondering is if it's chronic pain.
What?
Okay.
Chronic pain. So again, these are motor vehicle accident survivors, and in addition to trauma-focused stuff, a good portion of these folks are coming in with chronic musculoskeletal pain, which is hugely disruptive in terms of all sorts of things. I might wonder if we have a high pain group that are just lower that's contributing to marital satisfaction, and a non-chronic pain group. I don't expect you all to know that. What I want you to do is like, hey, there's a bimodal distribution here. It could be something going on. But sort of doing this work, I would maybe hypothesize that maybe we have a pain effect going on here, which are 2 very distinct populations, right? That we've merged together. We don't see it necessarily, or maybe we do in the men, right? It's just hard to know just because we don't have that many scores. Okay. So wanting to go through and take a look, again, certainly not normal, but we're working with a limited number of observations, so we have to be realistic in terms of what we would think. But in terms of crazy outlying values, do we have any concerns about these? No, it's not normal, but we're too worried about something dragging my mean around, okay? Same thing with my box plots across men and women. We see marital satisfaction, median value lower for men than opposed to women. This is just a straight symmetrical thing going on here. We see maybe a little bit of skew sort of in that box plot there, but again, no values falling beyond 1.5 times the interquartile range. So we're pretty good with this stuff. Okay. Same thing if I drop down in the Marlowe Crown, I've only got 5 people, so we're not seeing too much there. Same thing, some negative skew here, but again, with only 21 women in the sample, we're not gonna expect too much out of this. We might talk about, you know, maybe some evidence of small, slight negative skew, which we already know, we've got a skew value, we're just kind of seeing it represented here. Again, if I go down and take a look at this, I don't want it to make too many conclusions about distribution of men just because I've only got 5 guys in here. But again, sort of median value, sort of interquartile range trends toward the lower here, maybe a little bit of negative skew, but again, nothing extended beyond 1.5 times the interquartile range. And so, but again, remember that there's, with each successive graph, it's not necessarily that there's anything new or shocking coming up, but it's just giving us a different look, a different way to go through and visualize the data that we have. Okay. So, gone through, taking a look at our distributions. Last thing I'm gonna do is I'm gonna go through, I'm gonna pull some magic here, okay? All right, so we already have, what I wanna do is I wanna look at distribution of my z-scores across my 2 groups, right? Now I could go through and run and hit sort of analyze, sort of go back through the whole pull down menu, or I could just grab that descriptive statement and drop this down. And you remember when I split my scores, it gave me z-scores for both my men and my women, and SPSS just turns sets a z in front of that. So I could just go through and say, give me z, Locke Wallace, z, Marlowe Crown, erase that save statement, just so I'm not saving z-scores, or I'm not creating z-scores out of my z-scores, because that's not a useful thing, right? I don't need skew and kurtosis. What's the skew and kurtosis my z-score is gonna be equal to? Same thing as that we're in the regular distribution. It's not gonna change anything there, right? I'm just wanting to go no min and max, right? So what I'm gonna do is I'm gonna, because I sorted to unsort my or to ungroup my variables, I'm gonna paste that sort command down here. And then I'm just gonna run this whole thing. So basically, what I could have done is I could have gone through and gone data, split file, paste, and sort of do all that stuff again. And then I could have gone through and gone analyze, descriptives, not undone that, put that in, go to options. I don't need skew and kurtosis, continue. And if I were to paste that, it's just what I had already, right? So you can go through and manipulate syntax that you've already gone, just to go through and get it to get, you can do it the long way, you can do it the short way. Either one, it should give you the same thing, yeah. Okay.
Oh, mine's like staying black and bolded.
Same.
So mine.
Just press
It's still
enter.
red though, but yeah,
Okay.
mine's black too.
What's that?
I don't know.
Okay. Let's give this a shot and see. If I go through and do this,
Oh, mine did, yeah. Okay.
All right, so this is what we should see. Different for men and women, it splits up, right? The other thing that you always want to do, because you'll mess it up at least once. If I've done this correctly, what do I get for the mean of my z-scores? Exactly 0. Standard deviation, exactly 1. If it's anything other than exactly 0 and exactly 1, you've done something wrong. Now, Johnny, when you go through and run this in Stata, this will give you a crazy exponential thing that's basically catching random digits in the end. That's like sort of 2.3 to the 50th decimal place, but zeros and ones. This is how you know, because what happens in what you'll do is you'll run your descriptives and save z-scores and forget to go through and sort or split your file. And then if you go through and take a look at your z-scores and these aren't exactly 0, you'll know that you've done something incorrectly, right? So you always want to make sure you split your file before you save those z-scores, because then that's taking the deviations of men from the average of men and the deviations of women from the average of women and creating those. So we're seeing that we've done this correctly. weapon I ticked on for a while. Gabe, what are we saying in terms of, the minimum and maximum statistics here? Do we have concerns about extreme values?
So, but
I don't think so either, but how do we know? You telling me you don't think so in a screening report doesn't give me tons of confidence. How do we know that what are we looking at that would reassure us that we maybe don't have anything too terrible in terms of extreme values based on what we're seeing?
not really sure actually. So,
Yeah.
Is it the min and the max
Yeah.
statistic?
Yeah.
If it's over 3, if it's over 3, that's like when it's like, yeah.
Yeah, right.
Okay.
So for this one, we started because we have such small scores, and this is where we need to be flexible in terms of thinking about within context, everything within context, right? If I've got a sample of 5 and I have something that's close to 3 standard deviations from the mean, I might get a little bit worried about that because that's gonna start to go through. If I have a sample of 150 and I have something that's 3.5, I'm probably not gonna worry about it too much at all, right? But here, everything is within about a standard deviation above or below, right? And so this just gives me an objective metric that I can qualify the extent to which my scores are spread out or close together. Here, nothing too concerning, but again, I probably already knew that because I've looked at the histograms and things along those lines. So again, none of this is shocking. It's just giving me tools and language to go through and communicate. Again, putting on that consultation hat, right? If I'm going to go through and run someone's data and say, hey, these are the things that you maybe should or shouldn't be concerned about, ways to go through and put objective criteria to that, or at least objective criteria used to contextualize things as opposed to just saying, yeah, it doesn't look bad, because I don't think so, right? You're not wrong, but what we want to do is just be able to communicate very clearly what I'm basing that decision on, okay? So if we go through and we run and we take a look at our screening report here, right? And again, thinking about this as you delivering this to a client, right? You're saying, found a missing score, got rid of that person. So it's a woman's case number is 132, just so people know what group that came out of, right? No problems with accuracy, plausibility, end up looking at 26 cases total. Here, talking about men, sample size, talking about skew kurtosis, sort of stuff going on here, talking about women, distributions of both of our distributions here, talking about box plots, so just kind of separating this out so we can kind of go through and there's not much to talk about here. You're just kind of sort of going through and providing a description. Here, outliers, extreme values, fail to provide strong evidence of univariate outliers or extreme values on either for both male or female subsamples, right? So we got to look at those separately. All this, we're separating things out. Homogeneity of variance, we're going to get to that in a moment. And then our recommendations, right? Missing is minimal. Despite the small sample, we lost 1 person, so not too bad. Design is noticeably unbalanced, right? We've got 4 times as many observations among women than we do men. So that's going to start to create some issues. We want to note that evidence of strong negative kurtosis in males, probably the result of just having 5 people in there. So just kind of contextualizing that. And then we'll get into Levine's test, suggest possible violations of homogeneity of variance and social desirability, but we'll see that when we pop up when we actually run our analyses, okay? So we're going to say anomalies in the distribution of scores in male respondents likely attributable to small sample, although we do have a notable discrepancy in sample size. Suggest also the possibility of unequal variances in social desirability, particularly given the limited power of Levine's test. We'll talk about that in a moment. Mean comparisons can proceed with caution, recognizing that these data likely underestimate variability in marital satisfaction and social desirability, particularly among male survivors. Why am I saying that? Why am I saying that we're likely underestimating variability?
Single size.
There's fine.
Yeah, I've got such a small sample, right? Probably variabilities in accident survivors is gonna vary by quite a bit, but if I only pull 5 people, where are those 5 people most likely gonna come? Right from the middle of the distribution, so important to go through and think about these things, okay? Recommend analysis of differences in social desirability, also use corrected tests to account for possible violations of homogeneity variance, right? So just kind of pulling all this stuff together. As we start to do this, it starts to become more and more information of trying to go through and synthesize this and make recommendations. But again, this is why it's important to think about what we're doing and everything in context, as opposed to falling back on hard and fast rules, because then we're gonna get confused and start to make recommendations that probably don't make a lot of sense. Okay.
As a seasoned researcher, do you write up a screening like this to kind of remind yourself in the process? Do you just hold this stuff in your head?
I kind of do sometimes, depending on what's happening. I mean, at this point, I have done it enough that I've got a pretty good scaffolding for what's happening, so I can go through and go, okay, so you need to think about this, or need to think about this. And so if you've done it a while, it's easier to keep multiple things in your head. But if it's a project I'm working on with other people or things like that, I might sort of put this down and be like, hey, this is kind of the things that came up in the data, things that we should be thinking about. This is why I made these decisions. Like, these are other things we could do, but given the context, I feel like this is probably our sort of strongest approach and sort of doing some of this stuff. So, and I don't expect you all, this is more kind of thinking about for a didactic. And so for me to evaluate and make sure that you're working through and thinking through things correctly, then this is a very, very valuable thing if you're doing like work for somebody else and trying to communicate like, hey, this is kind of what's going on. Something that you can use in terms of your own research to try to get a better understanding. In addition to sort of understanding stuff about my data or just assumptions, it's also just a good way to think about what the hell's going on with these data. Are they doing what I expect them to do? Is there different things going on, right? And a way to just kind of summarize that. So yes, you can use that flexibly once we finish. All right, let's take a break. Let's come back at 4, and then we'll jump into run through the t-test. Like, this is the thing that takes up all of our time. Run the actual t-test like that, and then we'll finish up the third sample. Ridiculous, but we're good to go. Okay, so we're working through all of these examples, but if you get behind and you're not super confident in sort of going through and doing things, those handouts, that's just, like, there's everything that you need on those handouts. If you just go through and follow and walk through those, that'll get you where you need to be. But if you want to go back through and take a look at actual walkthroughs, I guess one of the positive things that happened as a consequence of a global pandemic, we taught 50/60 all online for the 3rd years now. And so that's all a screencast on sort of a thing. And so all of the online examples that we're working through, it doesn't change from semester to semester all that much in terms of content and things like that. So what I'll do is add to our homepage a link to that season of Psych 50/60 that you can go back through. And if you want to go through and have those step-by-step walkthroughs, can go through, and it's the same thing that we're doing here. Okay. Does that help? Yeah. Okay, and it's just a nice resource to have. Grace, you can go back to, I don't know, like 5 or 6 years back and sort of watch like 6th or 5th years right now, should I go through and do stuff? Like, hey, John, remember that time you said that in 50/60? Do better things to do with your time than that. If you want to. Okay, so we've gone through and we've gone through, screened our data, got everything written up, right? That's really the bulk of the work. When we go through and actually want to run our analyses, all we do is go through, and I'm going to go to analyze. I'm going to go to compare means. Okay. And I'm going to go to, shut this down. It won't matter, but I'll just nuke that. All right, so I'm going to analyze descriptive statistics, or not descriptives, compare means. independent sample t-test. And I'm gonna choose my Lock-Wallace and my Marlowe Crown scores. Okay. And then we go through, I'm gonna take my gender, my grouping variable. Now, what we need to do here in SPSS is we need to define groups. If I had a multi-coordinates variable where there were sort of 1, 2, 3, 4, I can still use that to run my independent sample t-test. I just have to tell which groups to compare. We've only got 2 groups, but what I need to do is define these groups. So first group, I've got men is 1 and women is 2. 1, 2, that looks good. Oftentimes, generally, if you're coding dichotomous variables, 0, 1 is a better way to do it. For when we get into like some regression stuff, here it doesn't matter so much, but just a good practice to get into. Here it's 1 and 2, so we're fine with this. We're gonna hit check estimate effect sizes, and then there's really nothing. If you wanted to change, if you want like 99% confidence intervals, you could do that under options. We're not gonna worry about that. So we're just gonna go through and hit paste. Gonna run this. And then we're gonna get our output.
When you put in a new output, is that important?
No,
Okay.
doesn't matter. I forgot to grab it. I had to unplug everything, go down, get a different data set and come back up, so.
Wait, I got
a warning. I got a warning.
Yeah, why did you get a warning?
Did I do something right?
independent samples t-tests are not performed for gender because this variable is specified both as a.
Did you split your
The
files?
variable and
yeah.
as a split variable.
I'd split your file.
Yeah, that's what you,
Oh.
yeah. So this is an example. So if you try and run an independent sample t-test when you've got a split file on, it'll give you a bunch of warnings.
Oh.
Yeah, see, there you go. So if you just go to through and sort, just sort, it'll take that split file off and then we'll get it. All right. So.
And you'll notice that in the bottom right corner, it will say splitter time.
Let me read the whole thing.
It'll tell you where.
On the bottom right, you can say like
Oh, like down here.
file split, you're like right.
Okay. So we go through and look at what we've got here, okay? So our group statistics, this is just, always want to go through and take a look at this to make sure that it's reasonable, like it's on point with what you're expecting, okay? And then we've got our independent sample t-test, okay? So let's start with our Lock-Wallace here, okay? The first thing we're gonna see in this table is our Levine's test for equality of variances, all right? Now, again, what is our Levine's test telling us? What is this a test of? Okay, that my variances, do I have, is there some suggestion that I have unequal variances based on my 2 samples? So do we want this p-value to be large or do we want it to be small?
Large.
Large, right?
Yeah.
So if we, because I mean, we've got some corrections, but generally we would prefer to have this not rejecting the null hypothesis of equal variances, right? And so here we've got a p-value of 0.569, and so
It's not significant.
we're probably good. We don't have strong evidence here to suggest, based on the data that we've collected at least, that Lock-Wallace scores vary differently in our sample of male motor vehicle accident survivors and women. So we've got 2 lines here. We've got equal variances assumed, equal variances not assumed. We're gonna go through, follow equal variances assumed, because we haven't violated, don't have indication of a violation here. We have our t-statistic, our degrees of freedom, our p-value, right? Here's our mean difference, the standard error, and our 95% confidence bound, right? So Allison, what are our data suggesting about marital satisfaction across men and women involved in traumatic accidents?
Like there isn't, the data suggests we have evidence that there's a difference between their
Yeah.
scores.
We do have evidence that we have some evidence that there's perhaps a difference in the mean Lock-Wallace scores in these respective populations, right? We got a p-value of 0.033. Based on what we know about p-values, is that super strong evidence? Oh, Probably not, right? I mean, it's enough for us to claim evidence of a difference. So to instead claim like, yes, these data do appear somewhat incompatible with the null hypothesis of equal satisfaction. But in what direction? Who's scoring higher than who, Allison?
I was trying to think. The females are scoring high.
And if we go back up to our log Wallace total here, right? We see, and this is an easy thing to sort out, right? We see evidence of a difference, and we see that our women are scoring higher than our men here, right? We would say that they have about a 29 point difference. And our data are compatible with estimates of population differences ranging anywhere from about men scoring about 2.5 points lower to over 50 points lower, right?
And that's difference from the mean.
Yeah, differences mean the main differences here, right? Always you can sort of always want to go through and you make sure that you know what that confidence bound corresponds to. But if I go through and I take a look at this, right, it's clearly not corresponding to the mean values, right? It's looking at the mean difference. Okay. So we do have some evidence of differences in marital satisfaction scores across these two groups, right? What about for our Marlowe crown? If we drop down into that, Lindsay, and we're taking a look, what is our Levine's test suggesting here?
That there's likely not large differences.
Yeah, what makes you say that?
Because the p-value or the significance is 0.05.
Mhm.
So it's a lot smaller. I think it's closer to 0.05.
Yeah, which would suggest what?
That there's almost support for them for the null. It's just a little bit above 0.05.
Support. Okay, so remember, and again, this is where we get into our mechanisms of, so like,
Yeah.
would we reject or fail to reject the null? What is the null hypothesis here?
The scores are equivalent across genders.
What scores?
The Marlowe Crown social environment scores.
What part of those scores?
The mean.
It's okay, there we go. Are we testing mean differences here in the Levine's test? This is a test of what?
Oh, variance.
Variance, right? So we're looking at violations of homogeneity. Do I want to have a violation of homogeneity of variance?
No.
No, right? And so here we're testing the null hypothesis of equal variances across groups. And so we're pretty close to something. Now, is that less than 0.05? No. Was it close enough to probably be functionally the same? Sure. How do we feel about 0.05 as evidence against the null? Not super strong. What's the other thing that's kind of playing a factor into my interpretation of this?
The sample sizes are
Yeah,
really different.
Right. Based on what we've talked about, if I have a sample size of 26, is there a ton of power in that? No. So if I've got that small of a sample and I'm still getting something close, I don't know that I'm comfortable just like writing off and saying like, oh, for sure, there's no evidence of equal or different variances across these groups. So again, like what often happens, I'm kind of in a weird ambiguous situation. If I'm playing just by 0.05 rules, I'm like, no violation, cool, I'll move forward. But if I know what I'm looking at, I'm like, well, no violation, but it's pretty close. And I also know that sort of this test, just like any other test, is constrained by power. And for a sample of 26 to be able to find something different would have to be pretty different. And the fact that we're even close sort of starts to make me a little bit nervous that maybe there's something going on. So here, if you want to just play by, like decision tree rules, you could sort of interpret equal variance is not assumed. I might be, I don't know, I'm just gonna play it on the safe side and go equal variance is not assumed because, yeah, that's not less than 0.05, but it's pretty close. And I'm also working with a sample of 5 and 21. And so that's not a very strong test, right? And so this is where we just start thinking about what's going on in our data and trying to make the best decision with what we got. Now, when we go through and take a look, Does it matter which one of these we use functionally in terms of our interpretation? No, I mean, it's that these data are functionally incompatible with the null hypothesis or sort of 100% almost 100% compatible with the, not 100% is an actual percent, but these are very compatible with equal scores. If we go through, we see a difference of scores of 18.6 and 18.9, right? Like there's really nothing going on here, right? So at the end of the day, it doesn't matter probably which one of these things that I use, but I would want to sort of think through this carefully, and that's what I would want to see in sort of your sets. Okay. All right. So we go through, take a look at this. The other thing that we would do is if we go down through and take a look, we have our effect sizes here. Okay. Now again, Cohen's D, as indicated by SPSS, if you see here the standardizer denominator used for estimating effects, pooled standard deviation, Hedges G adds the corrected factor, glasses delta. This is, you have to be careful and know which. Be very careful before you interpret glasses delta that you know which is the reference group, right? So make sure you go through and look at that. So again, remember Cohen's D, this is what we've been calling Hedges G, right? Hedges correction, this is unbiased G, and this is glasses delta. You just want to make sure that you know which standardizer is being used here. Okay, so for these analyses, which one of these is going to be maybe your best choice for an effect size? Jim?
The Hedges correction,
Hedges correction, why do you say that?
because we don't care about Cohen. And then I wouldn't feel comfortable being like, oh, this is our control group
Exactly.
in this scenario.
Yeah.
So remember, we don't not care about Cohen's D because this isn't Cohen's D that I told you we don't care about. This is a different go. So this is actually Hedges G, right? So this would be using the pooled variance, but you say Hedges correction. Why would we want to use unbiased G?
Small sample size?
Yeah, we've got a pretty unambiguous small sample size. Now, if we look at our point estimate for Hedges and unbiased, is not that much, right? So it's not too big of a deal, but if we're being technically correct, we'll probably go there, right? So we have our point estimate here if we're using Hedges correction. So we've got almost a full standard deviation difference in numerical satisfaction across men and women here, right? And that's pretty substantial. SPSS is calculating our confidence bounds. Looking at our confidence bounds, what are we thinking about the confidence bounds there? For Hedges G, or for our effect size?
Kind of wide.
Yeah, yes. So we could have an effect size of anywhere from a little under 1/10 of a standard deviation unit to over 2 standard deviation units. This is something we'll get into when we calculate confidence intervals around effect sizes. It's different than calculating confidence intervals around means. They're much wider, right? And they will be really wide. And this suggests a great deal of uncertainty in these data based on the magnitude of this effect. This is our best guess, but there's a lot of uncertainty here. Yeah.
Is that what that means?
Mhm.
Like the effect size numbers, like that's talking about like standard deviation?
Mhm.
I thought we were just making things up and we're like,
No,
yeah.
No, we're saying, hey, this is the standard deviation
Wow.
units. I know, it's pretty slick, huh? Now it all comes together, right? I know. It's a crowd pleaser. All right. So, want to go through and, jump back into our into our slides. Okay, I'm gonna move through this pretty quickly. So we going through calculating this all in SPSS, right? So you have all that information here. Here's our output, what that's looking like. From this, if we were going to go through, this is me doing stuff before SPSS calculated all your effect sizes for you. Here's me calculating for Locke Wallace, your pooled variance and calculating G and unbiased G. Again, for Marlowe Crown, so it's just doing this all by hand, right? Just so you know how to do it. If the computer will do it, let the computer do it unless I tell you to do it by hand. But I also want you to know how to do it sort of long way so that you can go through and start doing this in research or papers that you've gone through and taking a look.
Will Will we be doing this long way on the exam?
Could be, I don't know.
That was my exact question.
Alright. So, going to, Johnny, this is gonna be stuff from, in Stata. Here, you're just requesting your homogeneity variance test. This, you're just requesting, your Levine's test. This first W0, it's creating 3 different Levine's tests. You're just gonna use this first one, right? And then you're gonna go through, run your t-test for men, or for your, for each of your things, right? So you're gonna get that, and then you can go PSYC 2 sample, gives you all your stuff. So what you're doing, instead of like an SPSS version where it just like dumps out like pages of output to you, with this, you're just asking specifically some more boutique, sort of like, hey, I want this, and going through and doing it, but everything should line up well with stuff here. Okay, so write up, all right. So again, here, independent sample t-test use compare satisfaction and desirability scores across male and female accident survivor diagnosed with PTSD. Null hypothesis, positive, no difference, right? So again, you don't need to have this in there, but it's just a nice way to kind of consolidate and sort of make sure that you're on the same page with stuff. This is a screening, ignore that, you don't need to worry about that, you've already done that on a separate page. Then here, trying to pull this all together, right? So we've got evaluation of Marlowe Crown scores failed to provide strong evidence for differences in social desirability across men and women. Again, we're just trying to sort of pack in descriptive statistics here, give their confidence bound and mean difference. Independent sample t-test identifies it is generally compatible with null or near null differences in these populations. Given assumptions of the underlying model, right? So this is talking about differences in social desirability. We don't have to go on and on about that because it looks like there's not much there, right? We say results do, however, indicate potential for greater level of satisfaction in female survivors with a point estimate of unbiased G, suggesting a full standard deviation increase in scores in women as compared to men. Again, we're just kind of packaging this all in here. Confidence bounds, however, identify values ranging from 2.45 to 54.84 as plausible estimates for the true difference across populations. And towards noting that the lower bound estimates supported by the data likely not consistent with meaningful differences, right? Given observed variability in the outcomes, right? Independent sample t-test also provides modest evidence for absolute difference in satisfaction in the larger population. Okay, so this is just us talking about independent sample t-test. Base factor, which we went through and calculated, 3.3 times out of no difference, 26% chance. So this is just sort of going through talking about base factor, S value, stuff like that down here, okay? So again, small and unbiased, unbalanced sample for the limits inferences that begin drawn, although data suggests possibility of greater marital satisfaction in women as opposed to men, strong conclusions regarding magnitude and generalizability require further study, right? So we're just kind of saying like, hey, this is what we've got. This is kind of what things are going on. Talking about evidence for differences, magnitude of that difference, right? And so again, we're kind of ambiguous here. Our effect size suggests quite a large difference. Our p-value says sort of evidence against the null, but not sort of super overwhelming, right? Precision on these estimates are pretty poor, right? We're saying that the actual difference in Marlowe Crown social or Locke Wallace is anywhere from about 2.5 points to a ton of points, right? So it's hard to get a good idea. Our best guess suggests a pretty substantial decrease, but we're really not precise with this, right? So just kind of pulling all this together to come up with an interpretation. And yeah.
I have just a question going back
Yeah.
to like the Levine's test, actually, so not even directly related to
Yeah.
this. But so if we would have had the like p-value of 0.054, but we had really large sample sizes, so like 300 men, 300 women, would we say that's marginal still?
I don't know, would we? So what happens if I have 300, 400 people, like say per group? What happens to the power of my test now,
It goes up.
right? And what's the null hypothesis? That there's no difference,
Right.
right? So this is an exact opposite situation where maybe I wouldn't be too concerned, like, because with that sample size, almost anything's gonna pop, and if I get something that's right there on the margin, also probably not gonna freak out too much, because sure, it's saying that there might not be exactly the same, but I've also got a hugely powered test, and so taking that into consideration. Yep, so we would do the same thing in the opposite direction, absolutely. Okay. All right, briefer, so if we were to write this up for publication, kind of what that might look like there, okay? All right, so want to finish up with some repeated measures stuff, okay? Our repeated measures design, what we're gonna do here is we're gonna look at the same group of participants on one or more variables across 2 or more occasions. And I've asterisked this because there are gonna be some situations, and this is some old school methodology stuff. If I use a matched pairs design, if I have one group and then another group that I've matched on a bunch of different characteristics, traditionally, or by convention, we would often use a paired sample test, even though it's 2 different samples. So that's some old school stuff. But generally what we're doing when we're looking at a paired sample test is we're taking everybody, one group of people, measuring them right now, and then we're doing something and we're measuring them again to go through and take a look at stuff, okay? Benefits of this, lots of the stuff that we look at in psychology and that we're interested in are sort of looking at people's response across time. Like, hey, I do this, I have this person, these are the characteristics, I do something and change it. It's a more efficient use of resources as opposed to having to grab this sample and compare it against this sample. If I can design a study where I just get this sample, I measure this sample again because I've already got them. Way more efficient use of my resources. And what we're doing here is we're controlling from random error. Remember, when I have 2 samples, I got 2 sources of error to address. When I only have 1 sample, it's just one sample, one source of error to address. What happens to my standard error? It goes down, right? Because there's only 1 source of error in there. I functionally have that. It ends up being a much, much more powerful test, okay? So lots of benefits to your repeated measures. Paired sample t-test, what we're doing is we're using to examine change scores within individuals measured across repeated assessments, okay? Here, underline this thing, the different scores are the units of analysis in my independent or in my paired sample t-test. What we're going to do is we're going to take time 2 minus time 1, and we'll talk about why we do it this way, and use this as my primary source of analysis. My output for my paired sample test are these different scores. What's the change scores across my repeated assessment? My hypotheses here. Null hypothesis is that the mean of my difference scores is equal to 0, right? If I measure you right now, and then I measure you later, and there's no change in your stuff, what's your difference score gonna be? 0, right? So my mean is that, or my hypothesis is that in the hypothetical population, if I were to take everybody who I'm interested in and measure them once, measure them again, what would the difference score be? Null hypothesis said there'd be no difference. There's no change in scores. Alternative hypothesis is that the mean difference is not equal to 0. Something happened, something changed across repeated assessments there. All right, and the question, actually from a conceptual standpoint, do different scores across multiple assessments deviate sufficiently from 0 to conclude a non-zero difference in the population? Like, it's never going to be exactly the same. Like, we're always going to say some shift, right? But what we're interested in is the level of shift that we're seeing enough to conclude that yes, there's likely some that hypothetical difference score in the population is something that's not 0. All right, so a quick example here. My t-test is going to be the mean difference minus the difference score assumed under the null. That's going to be 0, so it's just the mean difference over the standard error of the difference scores. Standard error of the difference scores is going to be the standard deviation of my difference scores over the square root of n, okay? This is going to be interpret the standard error of my difference scores is the expected mean difference in scores within individuals across repeated assessments, right? Like if I were to replicate this again and again and again and again and again, how much would I expect with the same sample size? How much would I expect those different scores to jump around across samples? Okay? So let's say down here, I've got a very small, I've got a study with 4 people, right? I measure people at time 1, I measure people at time 2, and then I have different scores, okay? I take time 2 minus time 1, get a 4-point gain, a 7-point gain, a 5-point gain, and a 2-point reduction here, okay? What I'm gonna do is I'm gonna take the mean of those different scores, the standard deviation of those different scores, And this is gonna give me everything that I need to go through and calculate my paired sample T. And so again, what's the question here? What's the probability of obtaining a set of different scores with a mean of 3.5, assuming that the null hypothesis is true? Okay. So this is what I'm saying when I'm talking about, so what's the input for your paired sample t-test? It's these different scores, okay? So do we really care about time one? Do we really care about time two? Do we care about how time one and time two scores are distributed? Not really, right? The only thing we're interested here is the difference scores. Now, I would probably want to take a look at time one and time two if it's my data, just to kind of see what the data are looking like. But for statistical purposes, all we're concerned about here are just these deviation scores.
Is it always gonna be time 2 minus time 1?
What happens if I do that? It makes the sign on that tell me whether or not I've got an increase or a decrease. You don't have to. You can do it the other way. You just want to be able to know, make sure you're interpreting things correctly. If I subtract 2 from 1, then things that are increasing are positive and things that are decreasing are negative. It doesn't matter. It's sort of interchangeable mathematically. It just makes your results that you'll get more intuitively. But if you don't do it, just make sure you flip it in your head so you know whether or not we're talking about increases or decreases. All right. Any of this stuff look familiar? Essentially, what are we running here? What is it, Johnny?
Single sample.
Yeah, all we're doing, like, there's nothing special or exciting or different or new about a paired sample test. It's just a single sample t-test testing against an assumed value of 0, right? We've just got one column of scores, just different scores. Are these different scores different than 0? This whole thing is just a single sample t-test using different scores, okay? But the thing that makes this so powerful is everybody starts to be their own controls with this. And we've only got one source of error as opposed to 2 sources of error in terms of this, an independent sample test. And so these are much, much, much more powerful tests than we would get with our independent sample stuff. So my formal assumptions of my paired sample test, again, outcomes are continuous. Sampling distribution of different scores in the population is normal. Don't contain outliers. Basically, it's all the same assumptions of my single sample test. We're just using different scores as opposed to observed scores on something. All right, and then on my auxiliary hypothesis, I just keep up is hopefully this sears in your brain, like, okay, these are the things that we talk about, but in the background, these are all things that start to impact my confidence in my inference. Okay, so effect sizes, just the mean difference. This can be a very effective sort of way of going through and thinking about things depending on what I'm looking at. If I have a metric that has some sort of intrinsic meaning, I can just sort of look at changes in, let's say, well, if you're looking at like jury confidence or something like that, like that's something that what percent are you confident that someone's guilty, right? If I see like a 50% reduction, that has some meaning to me, and that seems pretty big, right? So we can go through and use some of this stuff, but then we can also go through and calculate our standardized effects, right? So Cohen's d here, again, we only have really one, well, we don't, we have a couple of different variances we can use. We can calculate what we might call Cohen's d here, where we use the square root of the average variances across 1 and 2, okay? Now here, remember, for when we were using our independent sample test, we use a pooled estimate. Do we have to worry about a pooled estimate here? Why not, Johnny?
Because it's the same.
It's the same sample. Like I don't have to weight anything, because if I've got someone who's only got scores at time 1 and not at time 2, then they're not in my test anyway, right? So I can go through and I can take the average of the variance across my 2 time points, take the square root of that, and that's going to be my standardizer. The thing that I need to be careful of, knowing that that what you want to do here, so your average variance is equal to your pooled variance here, but the square root of your average variance is not the average of your standard deviation. Okay. So what you don't want to do, what you always want to do is when you're doing this, you want to work with variances, right? So I take variance at time 1 and variance at time 2, and I just take the average of those variances, and that'll give me an average variance. And then what I do is take that average variance and take the square root of that. And that's gonna give me my estimator here, okay? What I don't do is I take the standard deviation, time one, standard deviation time two, and take the average of that. The average of my standard deviation is not gonna be the same as the average of the square root of my average variances. You've got some squaring stuff going on there. It's gonna be different, right? So when you're running calculations, always be working with variances as opposed to standard deviations for your calculations. So we've got this is essentially, this is functionally hedges G. This is functional hedges G is what this is doing. You're just taking an average variance here, okay? Here you can also have Glasses delta, same thing before. And Glasses delta is really nice for these pre-post designs because oftentimes like where I'm at baseline is kind of a nice comparison group. And so where I'm at down the road, right? So you've got this piece. And then you also see sometimes an R squared value reported for paired sample tests is taking the square of your T statistic over the square of your T statistic plus your degrees of freedom. This has less interpretive value here probably. So I'd be looking at sort of one of these two here with things. Okay. Yeah, Johnny.
What would make you choose one over the other in this situation?
Same thing as before. Do I have a nice is my sort of baseline a nice comparison group? It often is with these paired samples. And then Glasses delta is kind of a nice option. Okay. But if I don't, like if I'm just looking at sort of this group, sort of it's something I've compared this group after I've had them do some manipulation and then after some second manipulation, then maybe this is going to be the better option. Okay, so this is a conceptual question, purely conceptual, and then making arguments for that. All right. Other thing that we can do is I'm going to encourage you not to sort of use these at least right now. We can take your mean difference over the standard deviation of your difference, right? And that's going to give you a metric of effect. Problem is the standard deviation of your difference scores is hard to get a good interpretation of that, right? So like I'm having a half a standard deviation relative to variance, half standard deviation difference relative to the variance in my differences. It starts to get sort of fall in on itself and get a little bit redundant. But we'll talk about times when this starts to become relevant. This is a correction for repeated measure stuff. Don't worry about that. Just these are up here for you to look at and sort of know that they're around. Let's put a pause on these for right now. So then probably be considering between these ones. All right. So we're going to run through and finish up with an example. Here, what we're interested in is the impact of anger imagery on the regulation of subjective anger. Okay? We conduct a pilot to determine efficacy of some manipulation intended for use in a different project. So we've got this manipulation, we just want to see if it works, right? So following the collection of 0 to 10 baseline ratings of anger. 0 is no anger at all, 10 is sort of most intense anger, right? We have participants imagine a time in which they experience intense feelings of anger. Okay, so we measure anger, and we have them sit there and just kind of stew. And for 2 minutes, have them just think about a really angry memory. After that 2-minute period, what we do is we have them rate peak levels of anger. Like how angry did you get, right? So we've got peak or baseline anger, we've got peak anger. And then what we do is tell them to go through and stop thinking about the anger memory and instead imagine a time when you experience intense positive emotions, right? So following 20 seconds delay, participants are instructed to rate current levels of anger every 20 seconds over another 2-minute period, okay? And so what we're looking at is increases in ratings from baseline to peak anger during negative imagery and reductions in the subjective anger from the first to the final rating during positive imagery. We're using these as our measures of how well this is working. Okay, so we've got 4 variables here. We've got baseline anger, we've got peak anger, right? And we want to just go through to say, hey, does this go through and get people ramped up? And then we've got anger ratings at the start of our positive imagery and at the negative end of our positive imagery. Wanting to see, do we see reductions of anger with positive imagery stuff? Okay, so how many paired sample tests are we going to run here? Two tests here. Okay. So what I'm going to do, just so we make sure that we get through this, let me pull up my paired sample T screening, and we'll just walk through the handout here, okay? So what I'm gonna do, remember, what's my unit of measurement, or what's my output with my paired sample T-test? Difference scores, right? So what I wanna do for the screening, I could screen my time 1 scores and I could screen my time 2 scores, but at the end of the day, those aren't really what I'm interested in, right? What I'm interested in looking at violations of assumptions is my difference scores, right? So what I'm gonna do is I'm gonna go through and first run a couple statements here. I'm first gonna compute difference scores for peak minus start, and then final anger scale relative to my start, or relative to my first anger scale, okay? So if I go through, we can do this real quick because it's something a little bit in an SPSS. So if I go to my paired sample tests here, right? If I go to down my variable view,
Wait,
yep,
do we have to like go through like the variable, like the data and delete any?
yeah, we will in just a moment, yeah.
Oh, okay.
Yeah.
But we
So-
can do this first.
Yeah, we'll do this first. And so, I mean, we can go through, so we've got, things that I'm interested in is we've got our anger, our baseline anger, our start. And then we've got our peak anger. And then we have, subjective anger ratings across each one of these successive ones. So I'm interested in, for this test, my final rating relative to sort of the initial one when I start my, positive imagery, okay? So I can go through and look at anger start, anger peak, not missing anything, a subjective anger to start. Okay, it looks like case number 18, I'm missing a value. Same thing, 18, right? So we would mark down 18 that we're missing a value there and go through, we can just go through and kind of get rid of that person. They wouldn't show up anyway, but it's fine. Well, actually they would. Because what I would do is they would then be included in my calculation of peak anger to baseline anger, but not in my subjective anger at the end. So this would be an important one to go through and get rid of, so everything squares up on the front end. Okay. So what I'm going to do now, though, so before I can start my comparisons, is I'm going to go through what I need to get is a measure of difference scores. SPSS, when I actually run my t-test, it's going to do this in the background. I need to go through and get those scores so I can go through and screen my data. So I'm going to go to data, whoops, no, transform. The transform compute variable. And what I'm going to do is I'm going to create a variable that I'm going to call anger difference. And this is going to be my peak anger minus my initial anger. Okay. And then I'm going to paste that. And then I'm going to go back to transform compute variable. Instead of anger difference, I'm going to call this one recovery difference. And I'm going to take recovery 6, my final anger rating, minus my first anger rating. Okay. And then I'm going to paste that. So if I go through and I take a look at my syntax, what I've got, and you'll see this exactly the same thing on your handout, just two statements here that are creating my difference scores, right? And because I'm taking the final rating minus the first rating, the signs on those, positive are going to be increased, negatives are going to be decreases, right? So I'm going to go through, run these. Everything's looking good here, and so I should see now in SPSS, I've got columns of difference scores for the difference between baseline and peak anger, and then I've got recovery difference scores taken from the initial rating from my positive imagery to my last image there, or to my last rating there. So I've got 2 sets here. Okay. And then what we're going to do is just basically run a single sample t-test screening for those different scores. Okay, same thing we did before. Do we need to worry about splitting file? No, because we just have one population of different scores. We've got a couple of different metrics, but screening is pretty easy and straightforward. Okay, so we go through and we run our descriptives, we save and go through and take a look. Any concerns with our skew kurtosis values here?
Not really.
Not really. In terms of looking at my anger difference, I'm seeing the mean value is positive, suggesting that, yep, people are getting more angry, for recovery. I've got a negative value, not quite as big, but it looks like things are at least going in the right direction with stuff. So that makes me happy. Go down through and I request my, histograms and box plots. Anything here that we're necessarily seeing as problematic? Not really, right? We've got kind of a nice normal, a nice kind of symmetrical distribution with something pretty big there on the end. We got a lot of people who look like they very much responded to this anger manipulation, right? We got so a bit kind of a high point of people reporting 8-unit increase in anger scores, right? But nothing that's too far out in terms of things here in my box plot. I look at my recovery scores. Things are looking okay, but what's kind of going on in the recovery graph? Anybody see anything interesting happening here? Yeah, we've got someone who's kind of falling away from the end of the distribution. What's going on with that person? What are we measuring here? What's behaviorally happening to this person across the positive imagery manipulation? They're getting more angry, right? If we go through and take a look at this, 0 is our mode. Like most people, the modal response is to not change at all, right? But we've got some negative skew here, and it sounds like sort of anger is dropping down. We've got one person who's getting more angry over the course of their positive imagery, right? And then we've actually got a couple more people here, right? What do we do about these? Are we worried about those folks?
Yeah. Could be.
Maybe,
Just like
I don't know.
random.
Maybe I go through and take a look and sort of in my hard copies of my data to make sure that those scores were recorded correctly, right? But is it fair to just start throwing people out of my manipulation because the manipulation doesn't work? Like, no, this is maybe gonna happen sometimes, right? But the thing is, when we're looking at our data, we wanna always think about like, what does this actually mean for the behavior I'm looking at? Here, it's looking pretty good, but we got a handful of folks where this is actually kind of making them more angry by a little bit. It's a little bit set off, but not too much. We're not worried about it from a statistical standpoint, but interesting, at least from a conceptual standpoint of things. Okay.
Blood pressure check.
Right? They don't, or maybe they just don't have faith. They just really sick people. They don't have faith. I've got nothing but angry memories in my head. That's sort of like, that's all I got going on. Okay. Going through and taking a look then at my Z scores for my different scores. Anything of too much concern here? Probably not, right? We've got so something about absolute magnitude, close to 2.5 standard deviations from the mean. Probably this is my or here, these are people where we're getting like sort of very strong reductions. This is my person who's kind of getting more angry, right? But overall, probably not anything I'm too worried about. Okay. So again, if I go down through and take a look, I've got missing case 18, missing values for subanger 1 to subanger 6. This is probably someone who, whatever reason, we lost data for. No problem about probable values, 42 people in the set. Looking at the difference in peak versus base, right? Differences in final versus initial anger, talking about some stuff here, outliers, extreme values, talking about stuff, and then you say, looks pretty good. So kind of a small sample, 42 is not huge, but for a paired sample test, this can actually be pretty powerful test. Okay. So we go through feeling comfortable with this. So what we're gonna do is we're gonna go to analyze. We're gonna go to compare means. We're gonna go paired sample t-test. And then I'm gonna go through, I'm gonna take peak anger, enter that first, initial anger, second. And I'm gonna take, for the next pair, I'm gonna take my final recovery score from my initial recovery score, right? Estimates of effect size, standard deviation of the difference. Remember I talked about standard deviation of the difference kind of being a weird metric to go through. So I'm gonna go through average of variances. and use that as my estimate of my effect size. But then the only other thing here, you got options, you can change your confidence bounds, but nothing much going on there, okay? So you all hit paste, I'm gonna hit okay. And again, if we pop open my paired sample stuff. What I'm seeing is here's my my mean values for each one of my things. So I wanted to go through and take a look to make sure that those are all consistent with what I would expect. Here's the correlation between my two. This is kind of interesting. Look at to what extent are my two scores correlated with one another. Interesting information here. We're seeing a much stronger correlation between recovery anger ratings than we are for the initial anger ratings. So that's kind of interesting information to note. Going down through, taking a look, do we have evidence for effectiveness of my manipulation? So we got the mean difference score. So here's mean on the initial anger activation. So we've got an increase of about 4.5 points associated with sort of lower and upper value for increase in anger ratings, a T value of 13. That's massive, right? And so very, very small test statistic here.
And that mean is like the difference, right?
Yeah.
The difference between like peak anger and initial and recovery.
Exactly,
Okay.
right? So pretty good evidence that, hey, if I ask people to kind of stew on an angry memory, it's pretty good at getting them ramped up. What about bringing them down, right? The positive imagery. If I look at positive imagery here, I've got a reduction. It's consistent with what I would expect. But boy, it's not much, right? It's about 1.5 points. My 95% confidence bound suggests anywhere from about a point reduction to a little over a 2-point reduction. And I've got a very, very small p-value. I got a really large T and a really small p-value. But I might wonder, like, to what extent, like, which one of these is looking like it's more effective? Getting people ramped up or bringing them down? Getting people ramped up, right? If I go through and I take a look at my effect sizes, sort of averaging across variability at time 1 and time 2, it looks like my for my anger activation, I'm getting close to a 2 standard deviation increase in anger scores. That's massive, right? Or excuse me, nope. Here we go. I'm getting over a 2-point, we're getting about a 2.4 standard deviation increase in anger scores by sort of taking people from baseline and getting them ramped up. This is a very effective way to go through, at least within this is in terms of looking at the way we've measured anger, looks like it's pretty effective. Now, in terms of bringing people down, we're getting about a 0.7 of a standard deviation decrease in anger scores, which isn't bad. I mean, we're getting close to a large effect here, not quite there, but sort of medium-ish, getting close to a large effect, but certainly not the same effect as we are getting people ramped up in that same 2 minutes. Okay, and then we've got confidence bounds around our effect sizes here. All right, so people are seeing kind of paired sample tests, beautiful. Love paired sample tests. Paired sample tests are fantastic and powerful. And they're actually really simple. All we're doing is single sample t-test on a column of different scores, right? And you can go through and do this if you just calculate column of different scores like we did for our screening, and then just run a single sample t-test. And so I have the reference value equal to 0, everything will come out the exact same, right? Just so long as you know sort of in our understanding sort of what's exactly going on with these things.
So is the standardizer piece in that table for the pair samples effect, that's the standard deviation?
Yeah, those are the standard deviation values that we're
Yep,
looking
and
for.
then the point estimate is the like how far we are from.
Yep, it's the actual, that's your, the point estimate, that's your actual effect. size.
Right, okay.
All right. So want to just sort of cut back here quickly. Okay. So this is just, we're going through running these in SPSS and Stata. All right, our write up here. Again, first part, we're just kind of talking about reorganizing and reorienting to what we're doing and why we're doing it and things like that. A nice way to start. Ignore this piece of things because you already got that outlined in your screener, okay? And then we're saying, here's scores collected in this pilot study, providing strong evidence against models specifying zero differences in the rating of subjective anger during negative and positive imagery, okay? This is me just talking like giving you different ways and different looks on how we can talk about this, right? Our model, our no model says no differences, right? And our data providing very, very, very strong evidence that that's not adequate to describe what's happening here, okay? 4.5 unit increase in subjective anger following negative imagery is consistent with the 2 2/3 standard deviation increase in ratings relative to variability at baseline. Here I went through, I guess I calculated glasses delta for this one to go through and do that. Data are compatible with anger ratings, right? So here we're just getting the confidence bound. Important to note that the lower bound estimate provided in this interval continues to suggest a 2 standard deviation increase in anger ratings relative to variability at baseline. So we're still, even at the lower end of the spectrum, this is still looking to be very, very large and very, very effective, okay? Point estimate of anger recovery, positive imagery models were modest, remains consistent with conventional benchmarks for a medium-sized effect. So here we're using D, and here we're using glasses delta. So I'm just playing around and using different effect size metrics, right? Because from baseline to peak, I've got a nice reference group. From peak where we got some people ramped up to where we ended, not really a good like base comparison control. So then we just switched over to D here, right? 95% confidence will provide support for clear and observable changes in subjective anger following both manipulations, although anger appears to have a stronger influence on, or anger imagery appears to have a stronger influence on subjective experience than does positive imagery. Okay, so just kind of tying all this stuff together to say something. Question is, ran a pilot, is this an effective thing? Data says it's pretty good. We have pretty good evidence. Maybe evidence for stronger effects one way relative to the other, but everything that we've got is very inconsistent with the null hypothesis of no change. So it's doing something. Yeah, awesome.
So for this, like you're looking at 2 different like tests.
Yeah.
But you have like one hypothesis where you're saying like the null hypothesis, so there's no difference. If there was like a change in one and not the other, how would you interpret that? Or like, would you need to break up your hypotheses?
Maybe, right? So I might just say like, hey, what we did is we found that asking people to identify, so to think about angry stuff really does a good job of getting people angry. Having them think about, once we've gotten them there though, once they're really cranked up, asking them to think about positive stuff, doesn't really have that much of an effect, right? We're not so we would say, yeah, go in one direction, super effective. Go in the other, not so much, right? And so just kind of decoupling and sort of thinking about like, what does this mean for what we're trying to do? Yeah, so just kind of splitting things up a little bit.
Just kind of adding on, like, how would you just phrase the null hypothesis for this?
The null hypothesis that the mean of the different scores, pre-post anger, induction is going to be equal to 0, right? Or something.
both.
Yeah. I mean, so it's just kind of think about the metric. What are we measuring? And like the question here is what's the population, right? And if we're going through and we're saying like, well, we want this to be for everybody. Well, we've just looked at undergraduates. So now all of a sudden, technically who I sampled from were undergraduates at the University of Wyoming. Who does this generalize to? And maybe as an add-on here, I might want to say like, well, sort of generalizability is in question because we certainly not have a representative sample of all people, right? And sort of starting to bring some of that stuff in. All right. I think just the last slide here. Strengths of our paired sample t-test. Okay. Again, this falls into some really nice types of questions that we have in psychology about how people change over time. Super efficient use. And we get reductions in my error variance because I'm only using sort of a variability off of one sample, right? Very, very, very powerful. Everybody starts off as their own controls. And so this is an incredibly powerful set of analyses. Problem is, it's not going to work for everything. If I have time-related factors, if there's just maturation that just occurs just because things happen over time, not only because of what I'm measuring, but because of other things. Then we've got problems here. We've got practice effects, right? If I give someone something once and I give it again and they already know the answers or expectations and things like that, it might be hard to go through and do this, right? We also have order effects, right? Like depending on which order I give people in, it might start to change things quite a bit. We can start to counterbalance order, but sometimes order is not gonna be all that helpful, right? Situations where these paired sample tests are maybe not gonna be, if you can use them, in the words of Dr. Zach Williamson, former graduate and sort of person in your seats, formerly in your seats, repeated measures are pretty damn slick. They are pretty damn slick. If you can go through and use this in your theses and your research, anytime you can incorporate a repeated measure, it behooves you to do so because they're incredibly powerful, right? You can tease out very subtle effects with these, but there's going to be situations where you can't, right? So just wanting to be aware that even though this is a really excellent way to go about through and test things, it's not always going to work, right? So just wanting to think about some of that stuff. Okay. So we've got our single sample T, just to pull this all together. This is looking at the mean of a continuous variable obtained from a single sample to a known population mean when the population variance is unknown. If I know the population variance, what can I use? Z-test, yep, single sample Z. If I know the population variance, cool, I'm back into Z stuff, right? But if I don't, which is usually the case, I'm down to a single sample T. Independent sample T, if I got two outcomes measured across two different separate populations that I've sampled from, and I want to see if whether or not the mean values are similar. Independent sample T, paired sample T, evaluating continuous outcome change across two occasions. Again, we're looking at different scores here from the same group of individuals. Again, the caveat there being traditionally we've got matched pair designs that we would analyze as a paired sample t-test, even though we're using two different groups, but we're saying, making the argument that those groups are matched. So functionally, these two people are the same except for whatever it is that distinguish the two groups, okay? But again, testing null hypotheses that the mean of the different scores in the population is equal to 0. All right, that's it. Questions, and if you need to sort of get up and go and take off, like we're done, but if people have questions about so where we're at, what we're doing, so anything with this stuff.
Not at this moment, and then.
Okay.
We'll come bother you.
I'll see you tomorrow.
Okay. Come by, sort of find me if you're sort of working with this, talk with Matt. Again, want you to have, and again, for these problem sets, try and sort of work this one is gonna be a big one. There's lots of stuff going on with this. What I want you to, so the best case is kind of like spreading this out, so they kind of picking at things as opposed to trying to cram it all in at once. You'll be able to do it. I have confidence in you, but sort of in terms of thinking about trying to get this stuff to stick and getting a deep understanding of this. These paired sample tests are going to be critical to, or sort of these means-based tests, these t-tests are going to be critical to everything else we're going to do for the rest of the semester. Okay, so just really want you to have a solid foundation. Okay, all right. Well, thank you, everybody. Thank you for all your work. Let me know if you have any questions, because we really want you to just be feeling really solid on how to think about these things. Again, the interpretation and some consideration thing is more important than how to get answers out of SPSS. That piece is easy. Okay, so thank you.
Yeah, are we going on our first official date?
I think so.
I'm hungry now. I'm hungry.
I have chippy guys, honestly.